Thank you. All right, so innate immune response. And so remember we said you're born with this, I said innate, didn't I? Adaptive immune response. We just finished innate, right, referring to the components that you're born with. You're born with your adaptive immune system as well, but it adapts and changes over your entire lifetime. So this is much more specific than your innate response. So this one develops the most effective means to eliminate an invader. The problem with this is it can take a week or more to build up following the first exposure, the very first time you're exposed to that specific antigen, because this is a very specific attack. So literally down to E. coli 0157, that strain, right? You would make a specific response to just that particular pathogen. In the meantime, your innate immunity must protect you, right? So that influx of cells, those neutrophils, those macrophages, they've got to keep it under control in time for this one to come online. And they have to help gather the intel that this system is going to need. The bad news is that sometimes your innate cannot keep it under control. And so therefore, you could potentially die, right, before your adaptive immune kicks in. The great thing about an adaptive immunity is its ability to remember, right? These memory cells that we've mentioned that you read about in the first web pages I asked you to look at. So the good news is that the second time they see it, they respond so much faster too, right? Because they've already seen it before. So upon re-exposure. So we take advantage of this memory component of our adaptive immune by doing vaccination. So when you vaccinate people, that may be their first exposure, and you're giving them a weakened form of the pathogen, one that should not cause disease. But it's going to elicit an immune response. It's going to get your immune cells to produce memory cells. So that way, if you see it again under natural conditions, your body's already seen it before and will respond much faster. You're not going to be waiting a week or more. The response, as I said, is very specific, right down to the molecular level. We're talking about recognizing, say, 10 amino acids within a protein. The specificity is very, very specific. In this system, though, it's very important, too, that we don't attack ourselves, right? So your cells that detect these foreign antigens learn the difference between healthy self, right, and something that's dangerous. And we say healthy self because there are times when your cells, right, are behaving badly and they need to be eliminated. Your immune system, under certain circumstances, can recognize when your cells aren't healthy and when they need to be eliminated. But also when we have invasion, right, when there's dangerous things. So we want to be able to recognize pathogens, ones that could cause disease. We want to recognize cancerous cells and eliminate them. So how do we do that? We have specialized cells, right? And this is from that first web page that I sent you guys to, right? Specialized cells that have specific receptors on their surface. So notice that this particular cell says this one fits. This is the bad guy, not these other two bad guys. Notice it's right down to a very specific molecular level, right? His little crown is what they're recognizing. That little piece of the bad guy, say it a bacteria or a virus. And again, later on, you'll have descendants of this cell that stick around. You'll have these memory cells. So as this guy says, I recognize, right? He remembers that one. We need to attack it. It's a bad guy. So you have two major components of your adaptive immunity. Your humoral component, which the major product of that stem of your adaptive immune is antibodies. So when people were first studying the effects of the immune system, there were components in your blood called antibodies, this humoral, this human element, right, that they were able to study. They're in fact proteins produced by your B cells, by your B lymphocytes. And they're specific to specific antigens, right down to the molecular level as you see the binding here. Those are really effective for stuff outside of our cells, right? So stuff in our blood and our tissue fluids, the antibodies can bind to them, help tag them for destruction by phagocytic cells. They can opsonize them, is one of the protective outcomes of your production of antibodies. But do all pathogens stay outside of our cells? No, some things have to actually get in order to take over the cell and get the cell to make more of itself. What does that? What's probably attacking me right now? Virus, right? Good old viruses, right? They have to get inside of our cells. Well, antibodies can't detect them once they're inside of our cells usually. We can detect them when they're outside and potentially stop them from getting inside. But we need some type of protection mechanism for inside of our cells. So cellular immunity, that makes sense, right? Cellular obviously means we're defending our cells, right? So that's a subset of your adaptive immune that specifically targets cells, right? Cells that may have gotten infected with viruses, bacteria, protozoa, anything that's an intercellular parasite, anything that gets inside of our cells, including when our cells, again, behave badly, right? When they're not doing what they're supposed to. We have the ability to recognize that. So because they work a little bit differently, the types of pathogens that they're effective against differs as well. And the cells that are involved, right? The specialists that are involved in these, right? There are certain ones that are used for humoral immunity that are not used in the cellular response. And probably one of the most fascinating diseases out there as it relates to the adaptive immune response is leprosy. For some people, they'll stay all in one spectrum. They'll just do an antibody response. This is referred to as lepromatous leprosy. And this isn't good because this is an intracellular parasite, right? So if you're just producing antibodies, you're only getting the ones that are outside of the cells. You have no defense against the ones that are inside your cells, right? So they continue to multiply inside your cells, right? And you don't have any defense against that. If you're all the way on the other end of the spectrum, which would be tuberculoid with just a cellular response, that's good, right? Because your cells are attacking the cells that are infected. But that's the one that typically will cause the deformities because they're actually attacking the cells. And this particular bacteria likes your peripheral nerves, right? So it'll infect the peripheral nerves, and so then the peripheral nerves get damaged by your immune system trying to eliminate the invader. That's two ends of the extreme. Do you think there's some cases where you have both a humoral and cellular response, an antibody and cellular response? Yeah. And so for that disease, some people fall right there in the middle, right? Where they'll have both responses. And then some will produce more of a humoral response and less of a tuberculoid cellular response, right? So they're skewed a little bit, but they're still getting some cellular response. There are some that'll produce a cellular response mostly and a little bit of antibody response. So there's this huge range of response depending on the individual, right? And of course, all this is determined by our genetics, right? What we're encoded with, how our system works. And the good news with leprosy is only about, they estimate about 12% of the population is actually susceptible to the infection, meaning that your immune system is able to take care of it. And meaning that you are getting more of a cellular response, maybe some antibody, but more of a cellular response. So sometimes you eliminate it even before you even know you're infected. It is spread respiratorily, we do believe, and armadillos carry it. Right? They get the same infection that people do. So leave them alone. One of my favorite stories when I did research in leprosy, and at one time they used to pay some of the lab technician to take samples from roadkill armadillos. And they're trying to determine how infectious they were, what the prevalence was in the environment. And this woman was from India originally. And so her and her daughter, it's raining out. The daughter's holding the umbrella, and she's taking samples off this roadkill armadillo. And a guy in a pickup truck pulls up. He says, "Ma'am, that particular roadkill is not good eating. They're diseased." He felt the need to tell this poor foreign woman, right, that she should not eat that particular roadkill. So, you know, the general populace, most people, right, especially the Cajun population that pretty much eat anything under the sun, right, they know that armadillos aren't on the menu, right? They're not on the menu. So that story definitely stuck with me. She was like, okay. She got the biggest kick out of it. So, this communication of sharing this information in your immune system is very important. It's very specific. And so remember before we've talked about what are the chemical signals, what's the general name we give to the chemical signals that allows these cells to communicate with each other. They're not hormones, that's endocrine. Cytokines, right? So you'll hear some cytokines mentioned in this, and I'm going to unmute this. I'm noticing it's muted. And let's see if this will play. No, because I don't have it plugged in. Pause. Rewind. This little thingy I gotta plug in. Let's see. That should work. Nope. That's because I can't get HDMI to work. It's not even playing in my headset, though. Oh, that's a bummer. Okay. I was really hoping to take a break from talking today. Well, oh, that's a good point. Thank you. So let me plug this back in and see, because I noticed that it is kind of low, huh? It's not making a it's not even playing. You don't hear anything up there, huh? Oh, look! So that's what it was. Thank you. Well, that's as loud as my computer will go. There we go. We'll start it over.
Activation of the immune response typically begins when a pathogen enters the body. Macrophages that encounter the pathogen ingest, process, and display the antigen fragments on their cell surfaces. Macrophages with antigen fragments displayed on their surfaces are called antigen-presenting cells. An antigen-presenting macrophage interacts with a T helper cell that can recognize the same antigen. During the interaction, the macrophage releases a chemical alarm signal called interleukin-1, which stimulates the T helper cell to secrete interleukin-2. Interleukin-2 causes the proliferation of certain cytotoxic T cells and B cells. The immune response from this point follows two paths, one using cytotoxic T cells and one using B cells. Normal cells of the body that become infected can also digest some of the pathogens and display antigen fragments on their cell surfaces. The body makes millions of different types of cytotoxic T cells. Each type is able to recognize a particular antigen. The cytotoxic T cells that are capable of recognizing the antigen displayed on the surfaces of infected cells bind to the infected cells and produce chemicals that kill the infected cell. Death of the infected cells results in destruction of the pathogen. B cells also come in millions of different types, each able to recognize a particular antigen. When B cells become activated by T helper cells, they differentiate.
I didn't even notice this for the longest time. I don't even know how long I used to show this animation. But right here, do you notice that this receptor is binding with this receptor? They don't really kind of match like the last picture. It's because they screwed up. It's supposed to be binding to this receptor. And that's slightly important. So, but we'll go over the different receptors and their different names, right, as we go through this unit. Just wanted to point that out.
T helper cells, they differentiate into plasma cells. These plasma cells become antibody-producing factories, flooding the bloodstream with antibodies that can bind to the antigen involved in this infection. antibodies bind to the antigens on the surfaces of the pathogens, marking them for destruction by macrophages. Some of the B cells do not turn into antibody factories, but instead become memory B cells that may survive for several decades. Because of these memory B cells, the secondary immune response to a future infection by the same pathogen is swifter and stronger. This powerful secondary immune response is what gives immunity to some diseases after you have had them once or after you have been vaccinated.
So that's what makes you immune, right? Is if you have this production of memory cells. The bad news is with some pathogens, right, you can't be immune because the pathogen changes. So an example would be gonorrhea. Gonorrhea is always changing its surface proteins, that bacteria that causes that infection. And so even though you may get the infection, you may develop an immune response, it's not going to save you the next time because the pathogen will look differently. The good news for that one is that there's antibiotic treatment, and you also do know how you get it, right? It can be avoided. It's called a sexually transmitted disease. Right? Okay. So, but this is also why you can get it more than once too, right? You don't develop an immunity to it. Other things you do develop immunity to, especially the things that we commonly vaccinate against, right? So your primary response is that first time you've been exposed. Now that could be via vaccination, right, or natural exposure. So for instance, when I was a kid, there wasn't a chickenpox vaccine. Chickenpox vaccine came out in 1995. Okay, so how did you get chickenpox when I was a kid? Your parents purposely took you over to someone's house when they had chickenpox. They were called chickenpox parties, right? So this was so that you would get chickenpox before you went to school. It's also so that you would get it when you were younger instead of when you were older. My little sister must have been the cleanest player on earth because she went to several chickenpox parties and she never got it until she was in high school and missed 2 weeks of school in high school. That's brutal, right? Especially at that level of education. And you can tend to have more complications the older you are. And then women, we have one more scary thing. What's that? Why do you not want to get chickenpox if you're a woman? Let me preface that. A woman with a particular condition definitely doesn't want to get if you're pregnant, right? Because it can pass through the placenta and affect the baby, either cause a miscarriage or infection of the fetus. So that's one of those ones that we don't want to be exposed to. Devontae, I'm going to pick on you today. Are you listening? Okay. We've had a lot of tardiness lately, right? It's kind of disruptive to the class, and I want you guys to make me a promise that you're going to work on it, okay? Right? I know we all have things that we do, right? But some of us are late every day. Right? Okay. So we're going to work on that, right? Okay. Good. All right. So that first response, right? If we get a good response, we should hopefully produce memory cells. Now they noted that for B cells, but this also happens for T cells, another subset of cells that they talked about. So that way, the second time we're exposed, it's usually those memory cells that are being activated, and so our response is much quicker. And as we go through the particulars of the response, it should hopefully make sense to you how important these memory cells can be. So humoral immunity really, as I said, can protect you against extracellular antigens, so the ones that are not inside of your cells. So bacteria when they're outside of your cells, toxins when they're outside of your cells, viruses outside of your cells, say in the bloodstream or in your tissue fluid. If it gets inside of your cells, that's when you need your cellular response. So definitely viruses that are inside a cell, it is the cellular response that's going to detect them and eliminate those cells that are infected. Both are powerful. Both can damage the body's own tissues if misdirected, right? If you have autoimmune disease where your immune system is attacking yourself, right? It doesn't recognize that it's you, right? That's the worst case scenario. So this is a highly monitored system, right? Verification is needed. We want to really make sure, right, that this is a bad guy if we can before we attack. And as I mentioned with leprosy, right, you can have both responses. You can have a humoral response and you can have a cellular response, or you could be stuck at one end or the other, which for some pathogens not really good, right? Especially for viruses. You don't want to have just a humoral response, right? Because that's only going to hopefully stop them from getting in, but once they've gotten into your cells, then you don't have that level of protection if you're not having a cellular response. It would really be beneficial to have both. Does that make sense to you guys? Okay. So we're going to start talking about the cells that are involved. And notice the cellular communication that was happening, right? Them releasing those substances like IL-1, right? That's a cytokine. It's an IL, it's an interleukin, right? White blood cells talking to each other. So they shows a macrophage in the video, and they can do antigen presentation, but your main presenters are your dendritic cells. So these are phagocytic cells just like your macrophages. They're going to gobble stuff up, but they really seek out your lymphocytes, your T cells to present this information to them. And there's two different types of T cells they can present. And there's two different types of presenting molecules that they use to communicate with these two different cells, right? So they have a specific communication. You can almost imagine it as a secret handshake. Dendritic cells and macrophages can talk to both types of T cells that we have. We have helper T cells and cytotoxic T cells. As the name implies for cytotoxic T cells, right, these are the killer cells. These are the ones that are going to attack infected cells and cause them to die. And this is going to be a specific attack. It's when the receptors that they have recognize, right, that this cell is infected with the specific target that they're looking for. Right? So in this case, they're specifically looking for maybe the influenza virus, the specific strain that you have. How do they know? The dendritic cell gobbled some up, processed that information, and presented it to T cells and found one that recognized this particular virus. And then they're going to produce a whole bunch more, and they're going to go out on a search and destroy mission, right, to find these virus-infected cells and eliminate them. Helper T cells, on the other hand, as the name implies, they help out other cells. They themselves don't directly affect any of our cells or any of the pathogens that we deal with. They help out. But again, they're going to carry this information from the dendritic cell about the specific antigen. And this is going to be something that's outside of our cells, which viruses are at one time or another, right? So you could get this response against viruses, bacteria, anything that at one point is outside of our cells, which is pretty much the case for everything, right? You should hopefully get a nice humoral antibody response. Helper T cells, therefore, as you can see, will help out the B cells. The B cells are the ones that make antibodies, right? These B lymphocytes, when they're activated by the helper T cell telling them, hey, this is the bad guy, I see that you know him too, and they're going to proliferate. Some of them are going to turn into memory B cells to remember this situation in the future. Others are going to differentiate into plasma cells. These will actually secrete the antibodies, as you saw in the animation. So they get really big. They increase their rough endoplasmic reticulum, because what are antibodies? What type of molecules? If we're increasing our rough endoplasmic reticulum, why is it rough? What does it have on it? Ribosomes, right? What do ribosomes make? Proteins, right? This is a secreted protein. It's mainly protein. It's a little bit of sugar associated with it, but predominantly it's a protein, right? So these cells need huge rough endoplasmic reticulums because they're going to make tons of protein that's going to be secreted by these cells. So they get really big. They're going to secrete these antibodies, and these antibodies are specific to the specific invader, right? So that specific virus, that specific bacteria, it will only bind to them. So as you see here, it's binding to a bacteria. When that happens, that alerts our immune system that this is something bad. So one of our common responses is, remember, when they're tagged for destruction, what we call opsonization, who's going to come up and gobble these guys up and kill them? Neutrophils, macrophages, more dendritic cells, these phagocytic cells, right, can grab onto these antibodies. They recognize that this is a bad guy because of the antibody present on it. And there's one other group of killer cells. Do you guys remember? It's a lymphocyte that can kill when certain types of antibodies are bound. It's in their name. Natural killer cells. Right? Natural killer cells can even kill antibody-coated cells as well by a special process. Macrophages, remember too, right? They're really important in killing and gobbling up and killing. So B cells will help activate macrophages even further, right? Increase their killing power when we know there is a specific invader. Also not shown here, once T cells are activated, they too produce memory cells. Right? So whenever these lymphocytes, B cells or T cells, are activated, you're always going to get memory cell production. So we're going to remember what we did, right? So if we come in contact with this invader again, the response is going to be much quicker and swifter, right? We're going to be really fast about it and very aggressive, right? It's going to be a much stronger response. So how do they interact? How do they communicate? Remember, it's all receptor, right, and molecular based. So B cells and T cells have specific receptors on their surface. For the B cell, it actually is the antibody that they'll produce. So it has that characteristic Y structure. But it can bind to antigens. And the difference between B cells and T cells is that a B cell can interact with antigen, notice, all by itself. The T cell receptor, on the other hand, can only interact with an antigen-presenting cell. It has to be presented by a dendritic cell, a macrophage, one of your body cells that have been infected. It has to be presented. And there's two types of presentation. And so there are two types of T cells that we saw, right? Helper T cells and cytotoxic T cells. And again, this is going to depend on what type of response do we need. Do we need a cellular response by the cytotoxic T cells? Or do we need a humoral response? And in that case, we may need the helper T cells to help out those B cells and activating that response and producing antibodies. So in addition to the T cell receptor, the T cells have a CD marker. CD stands for clusters of differentiation. This particular marker only binds with a particular antigen-presenting receptor. Right? It's a specific, right, like I said, almost like a secret handshake. The T cell receptor is what's going to actually recognize the antigen that's being presented. The CD marker is going to recognize what type of antigen presentation molecule is being used. There's two main types. MHC class 1, and that stands for major histocompatibility complex. And those molecules are the ones that create problems when we try to do tissue and organ transplants, because our cells can't communicate with each other. Because from person to person, your presenting molecules vary. So that's where it gets its name, because it was a major problem, right, when developing and trying to be compatible. But come to find out, the reason why it's so important is because your cells are using this to communicate with each other, specifically about antigens, about these foreign substances that are getting into your body and into your cells. So we'll talk about which ones match with which a little bit later. So where does this happen? Where do these dendritic cells and macrophages present this antigen to these B cells and the two different types of T cells? Well, there is a particular way of carrying this information throughout your body, because you don't want these pathogens getting on the superhighway, which would be your bloodstream, right? We don't want these things traveling to all different parts of your body uncontrolled. So we have a special system of lymphatic vessels. You could almost imagine these as our sewer system. They're going to soak up the extra fluid that ends up in our tissues when we have inflammation. That fluid could contain pathogens. Because of that, right, we don't want that fluid going back into circulation until it's been filtered and treated. The same is true for our drainage in New Orleans, right? And sometimes that system gets overloaded even when it rains out. But we don't want that pouring into the river, right? We certainly don't want our sewage going directly into the river, right? We want it treated and taken care of before it gets into the river. So the same thing in our body. We don't want pathogens to get a free ride all throughout the system. So this system is designed to trap, move, filter, and recognize the things that get into our system. So your lymphoid system, which is the reason why your lymphocytes, right, the B cells and T cells are named such, is designed to get them in contact with the antigen. What does that are lymphatic vessels, the secondary lymphoid organs, and the primary lymphoid organs is where the white blood cells come from. So you guys already know one primary lymphoid organ. Where do all your white blood cells originate from? Stem cells, hematopoietic stem cells that are located where in your body? In the bone marrow, right? Because remember B cells, bone marrow, right? Those receptors and everything know the difference between self and non-self when the B cells leave the bone marrow. So I always remember B for bone marrow, although that's not why they have that name, but it works out. Right? T cells, on the other hand, are given their name for the specific organ where they get their education. They have to leave the bone marrow and travel to another organ in order to get educated and all their receptors taken care of. Where does that happen? Thymus, right? So those are your two primary lymphoid organs, right? Your bone marrow and your thymus. Right. That's where they're born, is in the bone marrow, right? And for T cells, they're educated, right? Their receptors are all checked out. Your lymphatic vessels, shown green here in this diagram, is not like a circulation system. It actually starts in your tissues, right? And it collects all the fluid eventually into two ducts, your left and right lymphatic ducts, which dump into your subclavian veins. So eventually the fluid gets dumped back into circulation. But all along the way, especially in areas where there could be a large breach in your abdominal cavity because of your intestines, right? There are collections in your armpit region, there are collections in your groin region, there are collections in your neck region. These are referred to as lymph nodes. They are going to filter the lymph. The lymph only moves in one direction, from the tissue, up the body, or in this case down the body, right? Always coming together, coming together, coming together into these two ducts that are going to dump it back in. So along the way, it's filtered multiple times potentially by several lymph nodes. What's inside these lymph nodes? Macrophages, dendritic cells, B cells, T cells. This is where those interactions are happening, where these presentation is happening, where you're getting proliferation of B cells and T cells when they're being activated by these antigen-presenting cells, these dendritic cells, these macrophages. So that's why sometimes when you're sick, right, and in your neck you'll have swollen glands, those are your lymph nodes that are swollen, right? The doctor will palpate them, right? This is good news, right? If they're swollen, it means your immune system is responding, right? They might not be able to completely take care of the situation depending on the type of infection. Now, a lot of times they're going to be very tender, right? When he palpates them, you want to punch them, right, because they're real sore. That's actually a good sign. Lymph nodes that are swollen, right, or enlarged that aren't sore may potentially be cancerous, right? So in that case, you're kind of glad they're tender, right, and don't feel so great. So that's another problem, you know, especially women who deal with breast cancer, right? If they have the breast removed, depending on if the infection is spread to the lymph nodes, they'll have some of the lymph nodes removed. And because of that, later on when you have infections and stuff like that, sometimes they'll get fluid building up because you don't have that network there anymore that would have been draining and removing the fluid from that particular area. So that can happen, and that has to do with, as I said, removal of some of those lymph nodes.
Do your T cells and your macrophages, do they have to work harder when your lymph nodes are infected?
Right. So if your lymph node is actually infected, like the pathogen's growing inside your lymph node, then yeah, that would be a bad situation because you know, where you're producing the defending cells are getting attacked, right? And so that would be a bad situation. Right, before they can mount a response. So one example of an infection that's really bad for your immune system is HIV, right? Human immunodeficiency virus. It actually specifically attacks your helper T cells, right? So imagine, as we saw, they're important, right? Especially for your antibody production, right? Helping out those B cells, helping out your macrophages become better killers. So when you deplete that system, right, it depletes a significant portion of your adaptive immune response. And that's why eventually, right, if your T cell levels, your helper T cell levels decrease so significantly, you can get to the state that we refer to as AIDS, which just means acquired immunodeficiency syndrome, because at one time they didn't understand what was causing, right, people to have these particular symptoms of being immunodeficient. There's other things that can cause your immune system to be deficient. There are other things that could put you in what's called the AIDS status, but unfortunately AIDS has become synonymous with HIV, right? But in truth, they're not completely linked. But, you know, debilitating that component, and what usually actually kills those patients is secondary infection, right, where the immune system can't defend you. Anyone know the most common infection that kills AIDS patients? Pneumonia. Pneumonia. It's usually the one that gets them, right? So we have this protection, but obviously there are pathogens that get around, right, these levels of protection. And the bad news, too, with this particular system is it takes time. It takes anywhere from 7 to 14 days for you to mount a response, right? So in the meantime, your neutrophils, your macrophages, right, they've got to keep it under control. They got to contain it in that particular area, try and keep it from going system-wide. So your spleen, anyone know what it filters? So the lymph nodes filter the lymphatic vessels with the fluid that's in them that we typically call lymph, right? And that's all the fluid that went into your tissues during inflammation. It gets sucked back up by your lymphatic system, right, by this sewage system. And we're going to filter it, trap any pathogens. In the lymph nodes, we're going to respond. Similar thing happens in the spleen, but what does it filter? Blood. It filters your blood. It's the only organ you can actually continue living without, right? So if you lose your spleen due to injury or rupture from bad mono infection or some other type of infection, people don't do spleen transplants, right? You'll never hear of that. You can live without it. Some of the other functionalities that the spleen does, your liver takes over. But then you're down one level of protection, right? You don't have something specifically looking for pathogens in your blood, right? So you really are more susceptible to bloodborne pathogens than other people because you don't have a spleen. So your secondary lymphoid organs, we've already mentioned your lymph nodes, right? And they're scattered all throughout your body, large concentrations in particular areas where invasion can happen. You have several other specialized areas, and your spleen falls into a secondary lymphoid organ, right? This is where the contact is happening, right? Where antigens are being presented. Your tonsils, which only 2 of them are shown here, but you actually have more than that. These 2 probably represent the ones in your throat, and you truly cannot see them unless they're excessively swollen. And you have to really be looking down someone's throat to see them. They're in your throat. They're referred to as your palatine tonsils. And these are the ones that typically people have removed, right, if they can keep swelling up because they are in your throat. So therefore they impede breathing as well as eating. That little punching bag you see when you open your mouth, right, that's your uvula. It's part of your soft palate. It helps prevent stuff from going from your mouth up your nose, right, because your nose, the back of your nose, that part of your pharynx, your throat, is actually connected. And that's why right now I sound like crap, right, and why my throat is killing me, because I got crap dripping down the back of my nose, right, back of my throat. Probably due to some lovely virus that got me. So one of the things that might be responding to is my tonsils, right? They might be producing antibodies at this point, or maybe even cytotoxic T cells. You have an additional tonsil associated with your tongue, referred to as your your lingual tonsil. I have to say I've never heard of anyone having that removed or ever hearing it inflamed. I think it's a relatively lowly active one. One more in the back of your nose, right, in that back portion of your throat, in between your 2 eustachiary tubes, which lead to your inner ear, which is why your inner ear sometimes will get infected, and it's because your nose and your ears are connected, right? And when you're stuffed up, right, so are your sinuses, all connected to your nose, right? Once it gets in here, it can go just about anywhere in your head. It's horrible, right? So that tonsil is referred to as your adenoids most commonly, and it's actually only one tonsil. I don't know why it has a plural name. The other name you'll hear is your nasal pharyngeal tonsil, referring to in the nasal passage associated with the part of your throat that's in the back of your nose. This one can cause problems for individuals, especially for little kids if it gets inflamed a lot, because it can block those eustachiary tubes too and stop fluid from draining out of the middle ear. So for instance, for my son, he had about 80% of his adenoid removed when they put tubes in his ears when he was little. And come to find out, it was allergy, right? So once we got him on allergy medicine, he was fine and didn't have any more ear problems. So for some people, right, all this association, all this linkages can create some serious problems. So other places where we're going to come in contact, right, our skin, right, is the huge barrier. And so instead of having organs, we have tissues. We have sections within there that contain lymphocytes, B cells, T cells, macrophages. And they'll interact with antigens that get in. So we abbreviate that skin-associated lymphoid tissue as SALT, which is kind of funny because our skin is sometimes salty, right? MALT stands for mucus-associated lymphoid tissue. So this is all throughout, right, our respiratory tract, especially your digestive system. If you look under the microscope, right, those prior patches that they talk about, those are white blood cells, right? And they're organized in a way that they can grab onto antigens. Some of your cells actually specifically bring antigen in and present it to your macrophages. And then you have this area of B cells and T cells. And then notice the lymphatic system for draining away. So as I said, blunt-ended system, it's going to suck up that extra stuff that comes out of our capillaries, out of our venules when we're experiencing inflammation. So next time we're going to talk about antigens, and we're going to talk about them very specifically down to the molecular level. The other thing that we're going to look at are antibodies. So for antibodies, this is a general like stick figure that we usually typically draw. I want you guys to review ahead of time the different parts of the antibodies, right? Read in your book. The book's on reserve at the library. Look on the internet about antibody structure. I don't care. Just look at it ahead of time. Don't forget to be working on your Connect assignments, right? Innate is already up. We finished it. You should be studying it and working on it.